Dear colleagues, me as a presenter of the collective work from Odessa, Ukraine, I will present you this paper. When creating the information control system of the mobile and robotic system, it's necessary to solve a number of issues of sensor signal processing in real time and with limited computing resources. To date, the general approach to building such system is based on the concept of Industry 4.0, computerization and informatization of many research processes and industrial production has led to the emergence of the industrial Internet of Things. To create such system, it's necessary to have filters in the sensor signal processing channel that are capable to restructuring their characteristic by software or hardware depending on the operating condition, operating models, and the presence of interference to improve the efficiency of the system as a whole. The digital channel for sensor signal processing in mobile autonomous systems includes various filters. Basically, it's created on low order filters because this is due to the low cost of calculating the transfer function coefficients and the number of coefficients, the ease of setting or rebuilding the filters, moderate power consumption and processing time. For example, a first-order Butterworth digital bandpass filter, which is described by a second-order transfer function presented as the first formula on the slide. For the restructuring, it's necessary to calculate one filter in the numerator and two in denominator. There are three coefficients. With the fourth order of the bandpass filter, the transfer function on which is already described by the eighth order and presented as the second formula. For such filter implementation, 8 coefficients in the denominator and 2 coefficients in the numerator must be calculated. Fourth order digital filter have steep edges. However, the presence of a ripple in a bandpass and stop band limits this widespread of such filters. In addition, when working in real time, there are restrictions on the amount of time and time of calculating on the restructuring and duration of the transition processes. In this regards, it's more convenient to use first-order digital filter. However, it should be noted that all first-order filters have the same amplitude frequency characteristic, but the steepness of the fronts of the AFC is low. In the sensor signal processing channel, typical tasks are changing the cutoff frequencies and bandwidth, as well as the steepness of the fronts of the amplitude frequency characteristic. Aim of the work is to analyze the use of serial connection of the same type of digital filters and improve the approach for calculating the cutoff frequency of a new connection. Such a connection makes it possible to increase the efficiency of the information control system in autonomous mobile robotic system by reducing the bandwidth and increasing the steepness of the AFC. With a series connection of the same type, the bandpass filter, the AFC of the new connection is compressed as it were, while the cutoff frequency are shifted to the central frequency and the steepness of the AFC increases. The transfer function of the main bandpass filter is mathematically described as presentation on the slide. It should be noted that peak frequency of the AFC does not change in this case, and it's determined by the excitation. When multiplying the same type of the AFC or raising their degree, the level remains the same. But then to determine the cutoff frequency of the AFC of the new connection when they are connected in this areas, it's necessary to extract the root of the corresponding order from the level C. Here is the correspondence between the cutoff frequency of the main AFC of the first order and at the level C and the AFC when 5 same first order AFC are connected in series. This cutoff frequency are determined by the AFC, the parameters of which are known on the new level. To determine the cutoff frequency of the new IFC after connecting n filters of the same type according to the main IFC, it's necessary to solve the excitation. Then here is the graph of the dependence of the cutoff frequency when the same type filters are connected in this areas on the number of the connections. As you can see from the screen, the bandwidth decreases exponentially. In this case, it's possible to show how many times the bandwidth will decrease with serial connection. For example, when connecting 4 components of the same type, the bandwidth is reduced by more than 2 times, and with 8 more than 3 times, and 10 the bandwidth is reduced by 3.5 times. The implementation of this approach can be both hardware and software. The hardware implementation is based on a serial connection of n components of the same type. The main components is calculated based on the data flow and work mode. For example, cutoff frequency, bandpass, gain, and determined based on data flow. Such algorithm was implemented, but it turned out to be complex for implementation and operations. It required additional computation, although some components of these algorithms were pre-calculated and stored in memory. The algorithm was developed and a signal processing program was written according to the difference principle of the Atmega 128 microcontroller. This made it possible to reduce the hardware of the system since all sensors and are connected to the analog to digital converter, which is located in the microcontroller, and also to reduce the processing type of data from the ADC because it's on the same data bus with the processor. Bandpass filter include notch filters which don't pass the necessary frequency, but cut them out. By analogy with bandpass filter, in this case, there will be compression of the AFC. But when connecting in the series, the AFC of notch filter does not narrowing, but expands in accordance with the transfer function of the filter. The mathematical description of the AFC of the notch filter looks as shown on the slide. So, bandpass filter includes notch filters, which with the expansion of the AFC, the steepness also increases with the expansion of the frequency band cut out from the signal spectrum. This is not convenient in some issue since with in accordance the order it's necessary to narrow the cut-off band with an increase in steepness of the AVC. So that's all. Thank you for your attention.